Good morning, students. Welcome to the Aryabhatta PU Science College, Vinomanagara, Shumaga. Now, we are switched on to the expression for the potential energy of 2-point charges in the presence of electric field. In the previous classes, we have studied the equipotential surface of the point charges, dipole charges, and one positive, negative charges on two same charges you have studied. And this here in the next, that is further, we are going to study the expression for the potential energy of 2-point charges in the presence of electric field. There is an electric field. In the presence of electric field, we have to the 2-point charges. You see here, 1 point charge, another point charge is in between. Here there is an electric field is there. So in the presence of electric field, what is the total energy? What is the expression for potential energy? Potential is energy stored due to the charges. So that we have to study. So there is a derivation is there. Derivation is not needed, I think, here. So it is not given any time in any examination, even in the supplementary also, and it is in the preparatory also it is not given. So it is not important, this one. And this one is not important, but formula is very important. You have to rotate down. So derivation, that is write the expression for potential energy of 2-point charges in the presence of electric field. So that is electric potential energy is U is equal to Q1 V1 plus Q2 V2 plus 1 by 4 pi epsilon naught into Q1 Q2 by R. This you have to write down. So that is the expression for this energy. So this is in the presence of electric field, you see. So the electric potential energy is U1. Write the expression for potential energy of 2-point charges in the presence of external electric field. This is an electric field is there. Inside thus that there is electric field is there. 2-point charges here Q1 and Q2. So that is for the total energy. And where Q1 and Q2 is equal to magnitude of charges, R is equal to distance between Q1 and Q2, V1 is equal to potential at Q1, V2 is equal to potential at Q2, and epsilon naught is equal to permittivity of free space. So once again I am saying U is equal to Q1 V1 plus Q2 V2 plus 1 by 4 pi epsilon naught into Q1 Q2 by R, where Q1 and Q2 is equal to magnitude of charges, R is equal to distance between Q1 and Q2, V1 is equal to potential at Q1, V2 is equal to potential at Q2, and epsilon naught is equal to permittivity of free space. That you have to take down. And next one is mention the expression for potential energy of an electric dipole placed in an uniform electric field. See, electric dipole is placed in the uniform electric field. Discuss the maximum and minimum values. So electric dipole we have to place it in the uniform electric field. So that one is the equation for this is. So you see here, dipole means 1 Q charge plus Q charge minus Q charge is there. So there is in the field, there is an electric field is there. So in between this is that we have to mention the expression for potential energy. We have to find out. So U, that is U is equal to minus Pe cos theta is equal to minus vector P into vector E, where P is equal to dipole moment, E is equal to electric field, theta is equal to angle between dipole axis and electric field, U is equal to potential energy. This formula you have to write down. This derivation is not there. Here derivation is there, but it is not important. You have to take down this. So U is equal to minus Pe cos theta is equal to minus P into E, and P is equal to dipole moment, E is equal to electric field, theta is equal to angle between dipole axis and electric field, U is equal to potential energy. That one. Next, when the dipole axis is perpendicular to the field, when the dipole axis is perpendicular to the field means the theta is equal to 90 degree, and U is equal to minus P cos 90, and the cos 90 is 0, so U is equal to 0. So minimum values of or 0. It becomes a minimum value or 0. When the dipole axis is parallel to the field, theta is equal to 0, that cos 0 is equal to 1, that is minus PA, that is maximum value. So that is the meaning of this is in the potential energy. So in the potential energy, if it is normal, perpendicular, but this energy of this dipole is minimum. If it is parallel, then energy becomes maximum. But in the previous class of electric field, I have said in the previous second period. So that is the electric field, for the electric field, this one is maximum and this one is minimum. But in this here, the electric field, if it is if the electric field is perpendicular, then electric field is minimum. But in this this is potential energy because is maximum. Electric field is maximum when it is 90 degree, but potential energy is minimum. In this case, when it is parallel, the electric potential energy, so electric potential is maximum and electric field means minimum. So that is, I am comparing this question with the previous class question is there. So totally you have to write here, for the energy minus PE cos theta, when the theta is equal to 90 degree, U is equal to 0, minimum value. When the dipole axis is parallel to the field, then theta is equal to 0 and U is equal to minus PE cos theta is equal to minus P. That is maximum value that you have to write down. So this is an expression. Next one, explain why electric field inside a conductor is always 0. So there is a conductor in wire is there. So inside this conductor, that is the electric field is always 0 because electric field is only outside, not inside. So otherwise, free electrons would experience force and drift causing electric current. So this is otherwise free electrons would experience force and drift causing electric current. So electric field inside a conductor is always 0. So whenever you take a conductor, the field is only outside. Inside this conductor, you see in the thickness is there. Inside that there is no electric field. Electric field always resides only outside on the surface. So this is why this is a question. So that is otherwise free electrons would experience a force. Electrons, if the electrons experiences force, then the drift causing electric current. So it is always in the outside. Explain why electric field is always normal to the surface of a charged conductor. So electric field is always normal to the surface of the charged conductor. So this is an electric field. So it is always normal. There is a perpendicular to this. Or you can take here. This is a conductor. Around this, it is electric field is rounded here. So this one and this one. It is 90 degree. You see here. This one and this one is 90 degree. So that is. So explain why electric field is always normal to the surface of a charged conductor. That is, if E is not normal, it will have a component parallel to the surface causing the surface current. If it is not normal, then it causes a surface of conducting. So that is, it is always normal. Explain why electric charges always reside on the surface of the charged conductor. You see here, charges are always resides on the surface of the conductor and not inside. I have explained here. Because if there are static charges inside the conductor, electric field can be prevent inside it, which is not true. If the static charges are static, statics, then it is in contradiction to this our law. So that is because there are a static charges inside the conductor field can be prevent inside it, so which is not true. So this is the charges are always resides outside the conductor, on the surface of the conductor. Next one is, so these examples it is very, very important. This question is, so it is a cross question. In one more question it may ask. So very, very important here. You have to learn it. So what I am underlined here, very, very important. So it comes in the model question paper. So Next, explain why electrostatic potential is constant throughout the volume. So it is electric charges resides outside. Electric potential means potential energy. So that is, it is always constant throughout the conductor. Why? So toward the volume, its volume is fully volume. It is throughout this volume. Electric potential is always constant. It is so electrostatic potential is constant throughout the volume because of the following reasons. First one, electric field inside the conductor is zero. Electric field inside the conductor is always zero. No work is done to move a charge against the field. So is here inside the conductor, no work is done to move a charges. So that is, no work is done to move a charge against the field. No potential difference between any 2 points inside the conductor. There is no potential difference. Only the potential difference between the two ends only. Inside this conductor, no need of potential difference. No potential difference between any 2 points. So this is why the electrostatic potential is constant throughout the volume. So once again I am explaining. Electric field inside the conductor is zero. No work is done to move a charge against the field. No potential difference between any 2 points. So throughout the volume is constant. Next, write the expression for electric field near the surface of a charged conductor. Surface of a charged conductor is there. So what is the expression? It is a derivation is there, but it is not important here. So E is equal to sigma by epsilon naught into r cap, where sigma is equal to surface charged density. E is equal to electric field, n cap is equal to unit vector normal to the surface. So that is. Next one, what is electrostatic shielding? Electrostatic shielding, what is meant by electrostatic shielding? You have some experience in this electrostatic shielding. So you see here, in any cable wise, in any TV cables, so this is a TV cable. So in this cable, one copper wire is there. Around this wire, there is a insulation is there. And so this is insulation. This is the shielding. Shielding is there. So after that also another shielding is there. So this is an electrostatic shielding. So electrostatic shielding means electric field inside the cavity of a conductor is always zero, and it remains shielded from outside electric influence. This is known as electrostatic shielding. So the field inside the cavity of a conductor, you see this copper wire, cavity of the conductor, it is the field inside the cavity of a conductor is always zero. So this is a thickness, within that thickness electric field is zero. So it is to avoid from the external field. So for that a cable wire, a plastic wire, it is wounded there. So that is, field inside a cavity of a conductor is always zero, and it remains shielded from the outside electric influence. This is known as electrostatic shielding. To protect instruments and devices which are sensitive to electric field, and used in design of TV cables. In this TV cables, design is there. So this is an example for designing of TV cables. Is an example for electrostatic shielding. Its uses is, it is used in making of TV cables. One. Another is there, electrostatic field. You see the LED bulb. So LED bulb you can see here. So this is an LED bulb. This is an LED bulb. Say this is LED. If you just remove this, you can see some small bulbs. Within this bulb, like the filament bulb, gas is filled, but here there is no gas is filled. So this is on the semiconductor diodes. I have diodes. I have explained in the semiconductors in the 13th chapter. Once again I will explain in the 13th chapter. Now just information you have only know the electrostatic shielding. So this is the shield. If you remove this you can see the some shielding is very sensitive instruments. You see the sensitive instrument is there. So it is fixed here, and if you remove this sensitivity input, you see the red colored, that is IC, integrated chips, and it is a black colored capacitors. So those chips and capacitors are very sensitive to the electric field. So for that they are shielded from the mica or some special insulators are there. They are fixed there. They are molded by a special insulators, that is electrostatic shielding. So this is when the current is coming here, when the current the electric light comes out, there is a electric field around this. To avoid that electric field, this is molded here. So this is a special type of that is diodes. So special type of instruments. So I have explained here. So this is so what is electrostatic shielding? Mention its uses. If the field inside the cavity of a conductor is always zero and it remains shielded from outside electric influence, this is known as electrostatic shielding. Uses: to protect instruments and devices which are sensitive to electric field. Next one, used in designing of TV cables. In TV cables it is used. Mention the electrostatic properties of conductors placed in an electric field. When the conductor is placed in an electric field, what are these properties? I will explain here. Properties. The main properties are: inside a conductor, electric field is zero. Inside this any conductor you see, electric field inside it is zero. On the surface of a charged conductor, electric field lines must be normal to the surface at every point. The surface of a on the surface of a charged conductor, electric field lines must be normal to the surface at every point. So it is very normal. Normal is 90 degree. Field is there, conductor is there. It is always normal, 90 degree. Interior of a conductor can have no excess charges in the static station. Within this conductor, there is no charges. Charges resides only on the surfaces. Charges accumulates only on the surface of the conductor, not inside. If the charges becomes excess, it will accumulate on the outside and it jumps to the outside, not resides inside. So this is the interior of a conductor can have no excess charge in the static situation. Electric potential is constant throughout the volume of the conductor. The electrostatic potential is always constant throughout the volume and has the same value as inside on its surface. In the surface, any surface you see in this surface throughout this volume, this is same. The electric potential is constant throughout the volume of the conductor and has the same value as inside on its surface. So that's it. Next one, what are dielectrics? Mention the types of dielectrics. I have explained here, TV cable example. Dielectrics are non-conducting substances. They have no charge carriers. So dielectric means in between them there is a medium in between. So we can use the HCl and water also for the dielectric constants. So dielectrics are non-conducting substances. They will not conduct electricity. Non-conducting substances. They have no charge carriers. When the charges are there, they are not carriers. There are two types of dielectrics: polar dielectrics and non-polar dielectrics. Only we are studying the non-polar dielectrics. What are non-polar dielectrics? Give example. Non-polar dielectrics are those in which the centers of positive and negative charges coincide. These molecules then have no permanent dipole moments. Dipole means plus and minus. You see water molecules H2O. For H2O, OH minus H plus is there. H2O means OH minus H plus is there. This is one positive charge. This is another positive charge. This is a dipole. Dipole means two poles, plus or minus charges. In the same way, HCl is there. H plus Cl minus, it is Cl minus. This is one pole, this is another pole, dipole, plus and minus. These are dipoles. So molecules of water molecules and HCl are dipoles. So non-polar dielectrics are those in which centers of positive and negative charges coincide. Notice this is, you see here, OH and H plus there are coincide. H plus and minus becomes H2O. You see here, OH. Centers of positive negative charges coincide here. So that is OH minus H2O. In the same way HCl bond formation is there, polar bond, non-polar bonds you can see in the chemistry. So HCl means that is the example for this. Non-polar dielectrics are those in which centers of positive and negative charges coincide. These molecules then have no permanent dipole moments. They are not a permanent dipoles. They are temporary. That is, they have no permanent dipoles. So example, molecules of HCl, molecules of water. So these are from first to last question you have to write down here. And it is very, very important. You take it in the notes. And once again, I am explain the memorizing part. Next one is memorizing part. Each question and answers I will explain 3 times. Without seeing one time, with seeing one time, you have to write it in a rough. First, you have to see. By seeing it one time, you have to write it in a notes. Without seeing another time, you have to write it in a rough. You have to take. Okay. I will see in Next one is memorizing part. I will explain each question in 2 times, 3 times, and you have to repeat by seeing one time and without seeing another time you have to write it in the rough. So this question you have to write it. By seeing one time and without seeing another time you have to write it in rough. This one, and this one. So memorizing starts from this side, from second question, third question. So this is, explain why electric field inside a conductor is always 0. Otherwise, free electrons would experience force. Otherwise, free electrons would experience force. Otherwise, free electrons would experience force. And drift causing electric current. Drift causing electric current. You have to write by seeing one time and without seeing another time. You have to write it in a notes, in a rough. Yes. Explain why electric field is always normal to the surface of a charged conductor. If E is not normal, it will have components parallel to the surface causing surface current. If E is not normal, it will have component parallel to the surface causing surface current. If E is not normal, it will have component parallel to the surface causing surface current. So this is. Next, explain why electric charges always reside on the surface of the charged conductor. Because if there are static charges inside the conductor, if there are static charges inside the conductor, electric field can be prevent inside it, which is not true. Electric field can be prevent inside it, which is not true. Electric field can be prevent, which is not true. So see, this is next one. Explain why electrostatic potential is constant throughout the volume. So electrostatic potential is constant throughout the volume because of the following reason. First one, electric field inside the conductor is 0. Electric field inside the conductor is 0. Electric field inside the conductor is 0. No work is done to move a charge against the field. No work is done to move a charge against the field. No work is done to move a charge against the field. No potential difference between any 2 points. No potential difference between any 2 points. No potential difference between any 2 points. So this one. Next, write the expression. You have to write this expression by seeing one time. Without seeing another time, you have to write it here. And next one. What is electrostatic shielding? Mention its use. Electric field, the field inside the cavity of a conductor is always zero. The field inside the cavity of a conductor is always zero. The field inside the cavity of a conductor is always zero, and it remains shielded from outside electric influence. And it remains shielded from outside electric influence. It remains shielded from outside electric influence. This is known as electrostatic shielding. Uses to protect instruments and devices which are sensitive to electric field. To protect instruments and devices which are sensitive to electric field. To protect instruments and devices which are sensitive to electric field. Next one, used in designing of TV cables. Used in design of TV cables. Used in design of TV cables. Next, mention the electrostatic properties of conductors placed in an electric field. So, inside a conductor, outside field is zero. Inside conductor, electric field is zero. Inside a conductor, electric field is zero. On the surface of a charged conductor, on the surface of a charged conductor, on the surface of a charged conductor, electric field lines must be normal to the surface at every point. Electric field lines must be normal to the surface at every point. Electric field electric field lines must be normal to the surface at every point. Next, interior of a conductor can have no excess charges in the static situation. The interior of a conductor can have no excess charge in the static situation. The interior of a conductor can have no excess charge in the static situation. Next, electric potential is constant throughout the volume of the conductor. The electric potential is constant throughout the volume of the conductor. The electric potential is constant throughout the volume of the conductor and has the same value as inside on its surface. Has the same value as inside on its surface. Has the same value as inside on its surface. Next, what are dielectrics? Mention the types of dielectrics. Dielectrics are non-conducting substances. Dielectrics are non-conducting substances. Dielectrics are non-conducting substances. They have no charge carriers. They have no charge carriers. They have no charge carriers. There are two types of dielectrics: polar dielectrics, non-polar dielectrics. Polar dielectrics, non-polar dielectrics. Polar dielectrics, non-polar dielectrics. Next, what are non-polar dielectrics? Give example. Non-polar dielectrics are those in which the centers of positive and negative charges coincide. Non-polar dielectrics are those in which the centers of positive and negative charges coincide. The non-polar dielectrics are those in which the centers of positive and negative charges coincide. These molecules then have no permanent dipole moments. These molecules then have no permanent dipole moments. These molecules then have no permanent dipole moments. Example, HCl, H2O, molecules of HCl and H2O. These are. So you have to write it by seeing what I have explained here. you have to write it. All these write it in a notes and in a rough, one time seeing and another time without seeing, that you have to write it. Okay, best of luck.